Good morning, good afternoon, or good evening, wherever you may be. Welcome to the Panasas webinar entitled Accelerating NGS with Hybrid Scale-Out NAS. The webinar is designed to highlight the benefits of Panasas storage and its unique next-generation hybrid architecture within the context of next-gen sequencing workflows. My name is Andre Franklin. I'm a Senior Product Marketing Manager here at Panasas. Today's presenter is Geoffrey Noer. Geoffrey is the Vice President of Product Management at Panasas and a 20-plus year veteran of the storage industry. Jeff will talk about storage challenges in next-gen sequencing workflows and associated storage requirements. He'll also share the NGS challenges of one of our customers and the results they achieved after deploying Panasas storage. Additionally, Jeff will discuss several product specifics of the ActiveStor hybrid scale-out NAS solution. But before we begin, let's just talk about a few housekeeping items for this webinar. This webinar is going to last, the presentation portion, about 45 minutes. Afterwards, we've allocated about 15 minutes for Q&A. Make sure your phones are muted during the presentation and the Q&A. You're able to submit questions at any time during the presentation by going to the GoToMeeting chat window. There's a questions section on that part of the screen, and just enter your questions at any time during the webinar. We'll address as many questions as possible during the QA time. With that, I would like to turn the webinar over to Geoffrey Noer.
Thank you, Andre. So I'd like to start by providing a bit of an introduction to Panasas at a very high level before digging into the next generation sequencing specific and product specific parts of the webinar. Panasas is the leader in high performance hybrid scale out NAS, and one of the distinguishing factors for us as a company is that we've focused on not only high performance, but ease of use and manageability and enterprise-grade reliability in bringing a parallelism and high performance to the enterprise, really, from the beginning. So with Panasas, you see a combination of the characteristics that you would expect from a parallel file system, but also combined with what you would want in enterprise storage. And as you'll hear, this is one of the reasons why there's such a good fit for our technology in the life sciences market. Our product is called ActiveStor. It's an appliance model, hardware and software in one easy-to-use system, and that solution is now in its 5th generation in terms of the hardware platform. That's coupled with our parallel file system and storage operating system, Panasas, and Panasas 6 is the current version of that. The solution has been shipping since 2004, so this is while there's still a lot of innovation occurring, it's a very mature technology that's battle-tested in hundreds of customers worldwide, including a very large number in the life sciences market. The executive team here is one of deep storage roots at a variety of companies. We have over 130 employees. One of the people that I would like to highlight here is our founder, Dr. Garth Gibson, who's our chief scientist currently. He was actually the author of one of the 3 authors of the Berkeley RAID paper back in the 1980s, which gave rise to the RAID levels of data protection that everyone in the storage industry knows and loves today. He was also involved in creating object storage at Carnegie Mellon in the 1990s, and then founding Panasas to bring a lot of his innovation and invention into a commercial vehicle. We're privately held and VC funded. Panasas has been focused, as all companies should be, on growing its customer base and success of its technology. We're very fortunate to have a wide collection of loyal brand name customers. With scale-out NAS, one of the nice features for both our customer base as well as for Panasas is that there's a high repeat buy rate as customers choose to scale out their existing systems. We've been selling for more than 10 years into the life sciences. and have more than 450 customers overall in more than 50 countries around the globe. Here you can see some of our customers in bioinformatics, ranging from commercial companies like Merck, Bayer, Novartis, to government institutions like the National Institutes of Health, to university environments as well, genomic laboratories. So it's a widespread of both public and private sector life sciences customers. And in this range, you'll find everything from population studies of human genomes in doing cancer research to crop sciences, for example, to animal genomics in the context of raising pigs, for example, and cattle. So it's a very wide range from everything from agriculture to human disease studies and other areas. So if we look at the life sciences in particular, life sciences has a number of data storage challenges that are really quite unique to this field. And the reason for that is that particularly in the genomics space, the science is changing much faster than the underlying IT infrastructure, whereas in other segments, you actually see it the other way around. The IT is changing fast, and people are wondering how to adapt their business processes to the changes in IT. Here it's the other way around. The speed at which larger numbers of sequencers and the power of those sequencers is increasing, as well as the cost of doing the sequencing is coming down. All of those things together are leading to a huge amount of data being created, and that's growing at an exponential scale. So you basically have the rapid growth in the high throughput laboratory instruments really affecting the storage requirements at a rate that we don't really see in any other market. It's not, even though DNA sequencers are definitely the leading source of that growth, everything from mass spectrometers and microscopy and MRI, other types of instruments are also responsible for the growth. So even though I'm going to be talking a lot about next generation sequencing, that's by far not the only application of Panasas technology in the life sciences. And so speaking of genomics, some institutions are now sequencing thousands of genomes per day, and if you translate that into capacity, you're looking at hundreds of terabytes to petabytes of new data every day, and that depends obviously on the scale of the deployment and the size of the institution, but that's the upper end of what people are trying to accomplish. So if you simply turn to traditional enterprise storage solutions, where this leads is to inevitably to pools of storage where you have many different file systems, and the challenge of trying to keep your data evenly distributed across all of those pools. Every pool that you add, every additional file system means an additional storage system to manage, so the management costs go up. And of course, keeping all of that storage filled when you have a lot of separate file systems is very difficult. And so, the typical enterprise utilization rate of 40% for storage, it's probably not quite that bad, but it's still you're still going to be losing tens of percentage points of your capacity on average, and that just simply leads to higher costs overall. The other challenge that's really a new challenge for life sciences is that I/O performance is now an equal problem to capacity scaling. So in the past, genomics data in particular was primarily used as more of an archive rather than as active data. And the reason for why this is changing is because we're collecting a lot more data, and then we're doing a lot more ongoing analysis of that data. And so as you're doing, for example, population level studies, you're going back and you're accessing the data that you generated 3 months back, whereas before you might have generated archived in case you might want to see it again, but a lot of times you might not have gone back to that data very frequently. So between the increase in the scale of the analysis being done and the repeated access of that data, the data is becoming more active, and this is leading for the need for much more performance in the data storage to keep up with the rest of the IT infrastructure. So what does life sciences have in common with other industries? So some of those do lead into some common needs. First of all, the only real way to address these challenges is scale-out storage. Of course, we'd love that to be Panasas storage. There are other solutions as well, but from an architectural standpoint, it really does need to be a scale-out topology, because only scale-out storage allows you to seamlessly and non-disruptively add additional storage as you need it, keep up with the growth, and still have only a single system to manage. Part of that single system to manage is having a global namespace where you have a single file system no matter how big it gets. And then it's very important that namespace be accessible by compute servers from a wide mix of different technologies, such as Linux operating systems, Windows for ingest often, and even Mac OS clients. Another aspect that's important is the need for dynamic load balancing, because for the same reason that multiple pools of storage with completely separate file systems is difficult to manage, you also don't want to be filling up your initial storage, scale-out storage, adding an additional node, and then having all of your new data going to only the new storage and creating a hotspot. So being able to have the storage system rebalance the data evenly as you scale is a significant requirement. That's the only way that you're going to attain the performance levels that are required. And then finally, in terms of the topology and the protocol access, having a direct access from the compute client straight to the source of where that data is located, as you'll see, makes a big difference in what kind of workflows you can set up. With a legacy protocol like NFS or SMB, often you have to copy data locally to compute nodes before performing analysis, whereas in a highly efficient direct access mode, there it's possible to have the compute clients do the analysis straight off of the storage. And as you'll hear about, this is how GARVAN Institute was able to dramatically simplify their workflows. So with that, let me introduce the GARVAN Institute virtually, since they're not on the call with us, but they're one of the most important genomics institutes based in Australia, and they're focused on cancer risk assessment as well as diagnostics for children with intellectual disabilities. All very important research, and they have a variety of labs that are focused on everything from basic genome informatics to epigenomics and studying the genomic variation, performing data visualization and transcriptomics. So it's a variety of disciplines, all related to the life sciences. They're very aware of the progress that we've all made in the last 10 years. You look at the cost of sequencing the first human genome for $3 billion US, and 10 years of time in 2003, and now it's $1,000 and takes 3 days. So, what can you do with this, and how can we translate these advances into improvements in clinical practices? That's what they're focused on. So at GARVAN, the IT challenges that they were facing, of course, were exactly in lockstep with their need for scale, not only on the sequencing side, but also on their researching staff size. So they were one of the first organizations worldwide to deploy the new Illumina HiSeq X10 sequencing system, and each one is capable of sequencing 50 human genomes in a day, which is 1.8 petabytes of data per year. So, this is a phenomenal amount of data growth, and in addition to that, their research staff was increasing from 10 to 80 scientists, and they had some existing BlueArc storage that was being used for enterprise needs. They tried to apply that to their genomic work, and it was just completely unable to keep up with their performance needs. They also needed to provide the data storage in a way that avoided ongoing research, so those scientists didn't want to take a pause for a few weeks to get the new system in place, so being able to do it non-disruptively was key. And then it also had to take into account the particular constraints of realities of funding. And this is not at all unique to GARVAN. It often occurs that grants that are provided to genomics institutions are for cover hardware and don't cover personnel. And so in this particular case, there was no funding coming in to expand the IT staff. So the existing IT staff was a staff of 3. One person focused on servers, one person focused on storage, as well as a business analyst. And some of the high performance file systems, particularly the open source based file systems like the Lustre file system, can deliver the high levels of performance, however, have a very large management burden associated with them. And so this was something that GARVAN had to factor in as they were looking at the best solution for them, and ultimately be able to manage that storage with their existing personnel. So what did they accomplish with Panasas? So they deployed 683 terabytes of Panasas storage under a single global namespace, and this in combination with their new sequencing technology was able to increase their capacity by a factor of 50 times. So if you think about the amount of I/O performance, to match an increase in sequencing capacity of that nature, I think you'll agree that was certainly that data storage played a significant role in being able to keep up with that sort of an increase. We were able to boost the productivity of 80 researchers, and they were complaining about their existing BlueArc storage, saying that they were basically it put in a position of having to quell a user mutiny over painfully slow application response, and that Panasas arrived just in time. They also found that they were able to really minimize the management overhead, and that was perhaps just as important to GARVAN as the performance. So actually, in the end, it's their server cluster IT person that manages the Panasas storage because it's part of that workflow, and the storage person is continuing to manage some of their enterprise storage assets. So that's ended up working out very well from a management standpoint. And then in terms of the workflows, as you'll see, they were able to really simplify their workflow and have the number of steps over the Illumina recommended workflow. And this has saved a lot of time and bandwidth, allowing them to deliver results more quickly to researchers everywhere. So about those workflows. So if you look at these two examples, on the left is an EMC Isilon, maybe I should say Dell Isilon now, based workflow, and in this particular case, this is what Illumina recommends because they've had a longer relationship with Isilon than they have with Panasas. We intend to change that, but today that's the case. And with Isilon, what they recommended is actually ingesting the data to storage, compressing it, transferring the compressed data to the node that's going to do the analysis, decompressing it, performing the analysis, and then writing it back to the storage. So basically what you're doing is you're using the data storage as an archive, and you're doing all of the analysis off of the compute node that's running the analysis software. So you're never accessing the storage, you're never performing the analysis directly against the storage. For the Panasas-based workflow, this is simplified because we don't do any of that. Instead, the node performs the analysis directly off of ActiveStor, and all of the nodes can access all of the data directly from where it's located And this is high efficiency and high enough performance that you don't need to do all of these additional copies and the compression and decompression steps. And so this has improved. This has had a massive improvement in terms of time to results, as well as improving the total cost of ownership. So now that I've talked a little bit about what GARVAN has accomplished, let me talk a little bit about the solution itself and Panasas ActiveStor, so that you can appreciate why this technology has been such a boon for their needs. So Panasas ActiveStor is all about high-performance, hybrid scale-out NAS. It's based on parallel performance around a true scale-out architecture. By hybrid, we refer to the fact that this is a flash-accelerated architecture. So we use flash storage for small files and metadata, and large files go on hard drive technology. This allows us to route the cost in the dollar per terabyte based on hard drives, but still provides substantial acceleration for small files. Ease of use and manageability is, in our view, equally important. You can set up a Panasas system in under 10 minutes and have a parallel file system at your fingertips, which is really unique in the industry, because parallel file systems are notoriously hard to deploy and manage, whereas with Panasas, a lot of the innovation that we've put into the technology over the last 15 years has really been focused on the reliability and manageability, not only on performance. Performance in some ways is the easy part. If you get the architecture right, you get the performance. However, the ease of use and manageability, as well as the reliability, are far more complex and take a lot more thought and a lot more effort. And that's why you see other parallel file systems like Lustre being strong at performance, but not particularly strong when it comes to the ease of use and manageability or reliability. In terms of the scale-out architecture, a legacy storage system based on a file server head of some sort, and this could either be something like a NetApp with a filer. It could actually even be an EMC Isilon system where each node is a file server, and all of the transactions have to go through there with a shared back-end network. Regardless of the particular permutation of what the legacy storage looks like, you end up with bottlenecks with that file server where it has to perform a lot of different services. It has to serve metadata, it has to serve data, it also has to do RAID parity computation, so the data protection is also happening there. And all of those things mean that you have congestion and bottlenecks as you scale. And in some cases, in the most traditional deployments, you end up with multiple pools of storage that limit the manageability. In the case of a true scale-out NAS architecture, as Panasas delivers, not only do we have a true back-end scale-out topology, but also we have a scale-out front-end. So the protocol service is based on direct flow, is a completely parallel protocol that allows you to get all of the performance possible out of the storage. And this removes those file server bottlenecks and allows the storage to both scale cleanly as well as in a very manageable and reliable fashion. And with us, our metadata services are actually out of band, allowing the only communications going straight to the storage in the I/O path being reads and writes. So that's the key to a lot of the efficiency of the system. At a very high level, we're a multi-protocol system. So while direct flow, which I just introduced as being our highest performance option for Linux systems, and this is what you would want to do NGS analysis from the cluster, you would want to use direct flow, either over 10 gigabit over InfiniBand. However, for ingest, you're much more likely to be using SMB, which is the standard Windows protocol. And so you can use Windows to, for example, upload the data into Panasas, and then from your Linux cluster do the NGS analysis straight against the data storage using the direct flow protocol. We also support Mac OS as well, so OS X is fully supported, as well as any legacy Unix workstations. So pretty much no matter what you have in your IT environment, you'll be able to integrate it heterogeneously with the Panasas system. And ActiveStor 18 is our current model. So I already introduced the direct data access and the parallel data transfer, the flash acceleration. Linear scalability, incredibly important. The point that I want to make about the hybrid system, though, is that this is a solution that is not only great at large file aggregate throughput, but it's also outstanding for mixed workloads. And as you'll see in a couple of slides, this is actually a common characteristic for NGS. And we've also done this. We also accomplished this performance without any hardware RAID bottlenecks. So in the Panasas system with direct flow, the clients actually calculate the per file RAID parity and create the protected data inside the client, and then that data is moved across the network. So there's less to do for the data storage system, and the data is protected earlier in the process. So in terms of linear scalability, this is a proof point from one of our, actually this is a climate science customer of ours. They have about 200 shelves of our storage at this point. We did this test after they deployed their first 100, and we did testing up to 90 shelves. So here you could see perfectly linear scalability of both reads and writes of going from 10 to 20 to 40 to 80 to 90 shelves. And we would have even had 10% better performance than this if we had had more than 2 compute nodes per shelf. So and the other distinction that I would make is that we've actually further improved the efficiency and the performance in ActiveStor 18. So you would actually be expecting to see up to 220 gigabytes per second from 130 shelves today. So let's talk a little bit more about life sciences and the files that are stored. So of course, life sciences researchers are typically not file systems experts. They may have a PhD in biology, for example, but they're unlikely to be a computer scientist as well. And even if they are, that's not what they've chosen to focus their careers on. So it's really an unreasonable thing for data storage companies to expect that life sciences researchers are going to write and create sort of an optimal solution and design their data for the ease of the file system. That's not the way things work. And so, one of the consequences of this is that it's very commonplace to see tens of millions, hundreds of millions, sometimes even billions of files that are all very small. And while this is not desirable from a file system standpoint, it's very important that the file system is capable of handling small file performance. And we've recognized that this could be easily solved by applying flash technology in a useful way. So what we've done is we take the advantage of multiple tiers, and the first tier is really cache, which is RAM memory, and this is battery backed so that we can temporarily store transient data in the RAM cache. But then we look at the size of the files and the nature of the accesses, and metadata and small files are automatically stored on flash. Large file content is stored on disk. And this allows us to, again, from a total cost of ownership standpoint, have economics that are very rooted in hard drive technology, but performance that looks a lot more like flash performance. So if you look at how the University of Minnesota has deployed Panasas, previously they deployed several different types of data storage systems for different solutions, and this was really not advantageous, as you can guess. They had deployed Lustre for their scratch space environment, and they found a variety of problems, both in terms of reliability, which was probably actually the #1 reason that we ended up replacing Lustre in that environment, but also because they had the small file needs by creating a private cloud that all of their different research divisions were trying to accomplish. So not only genomics, but also CAE for product design and simulation, climate science, astrophysics, actually quite a few other disciplines. So they serve a private cloud with 2.4 petabytes of Panasas storage as one big global namespace, and they see the advantages with mixed workload performance every day. They've told us that we're the first storage system that they've deployed that actually delivers close to ideal performance for all of their applications, not only the large file environments. Ease of use and manageability is absolutely key. I know I've said that before, but I want to highlight that, in addition to being under 10 minutes to set up, and that's been validated by not only our customers but also analysts like ESG. We automatically recognize new storage when it's plugged in. When you log into as an administrator, it will say, I see you've added new storage. Would you like me to automatically add it to your existing file system and then automatically load balance all of the data so that it's evenly spread? You click yes, and it's done right away. So there's no modification of complex configuration files. There's no downtime. Everything is very easy. You have a simple management view from either a GUI or a CLI, and we provide a lot of advanced enterprise features, not only snapshots of user quotas, but you can integrate the system into your SNMP management tools. We even have a XML interface that allows you to script, to suck in some of the management data with your own scripts and bring those into your own management tools. So there's a tremendous amount of capability that's included on the management side. I want to touch on the reliability because this is one of the biggest differentiators for Panasas. It's all based on erasure codes and software, so we don't depend on hardware RAID at all. This allows us to actually deliver triple parity protection with our RAID 6 Plus technology and provide that in a way that is true high-performance access. Typically, when you go to even dual parity, but especially triple parity, with other solutions, the speed of the data storage will slow down to a tremendous extent. That's not the case with Panasas. We protect every file individually, which allows us to minimize the amount of effort that needs to be taken. In many cases, if it's just a range of, for example, a range of bad blocks on a disk, we only have to rebuild those specific files that are impacted. If even an entire drive fails, all of the other drives in the system, not just a RAID group, can participate in the rebuild. So being able to scale the rebuild performance linearly is key to minimizing the risk from the additional numbers. And then because we distribute data randomly, this actually allows us to increase reliability at scale, whereas systems that are based on hardware RAID arrays actually get worse at scale because of the way that the data is stored. It's basically, in a hardware RAID environment, it's one RAID level for the entire file system rather than being able to make that choice on a per file basis. And there's just much less intelligence possible from the file system because the file system and the data protection are separate. They're not. The data protection isn't built into the file system. And then finally, you may have heard about discussions about the number of nines of uptime of data storage and of server systems as well. We think that this is not the right way to look at things because you should be able to stay online even if you have a catastrophic scenario where too many hard drives have failed at once. And the reason for that is because if you've distributed your data properly, like we do with a random distribution, in a very large-scale system, the vast majority, for example, in a system with hundreds of millions of files, under 10 files will be impacted by a three simultaneous hard drive failure, one too many for RAID 6. So if you only have 10 files that are inaccessible, surely you want to be able to access the 99,999,990 files that are still intact. So we've invented an extended file system availability mode that protects directory structures deeper than the data, which means that even if you have a too many drives offline scenario that would be catastrophic for any other storage system, In our case, the storage system will stay online. You can still access all of the data except for the files that were actually damaged. And then you can rebuild those specific files. That may sound bad, but that's way better than being faced with multiple petabytes of data that all have to be restored. And in many other file systems, if you have any sort of a data loss from too many drives failing at the same time, you lose all of your data. With Panasas, you'll only have a very small impact, and we'll be able to tell you the specific files to restore, and you'll be able to restore potentially as fast as in minutes, if not in hours, whereas another solution on the market might take you weeks to rebuild. So you try to design the system to be the best in normal operating mode, but you also assume the worst scenario, and you also try to design a system that is resilient in all of the failure modes. And that's one of the things that Panasas has really accomplished with this technology. So I'd like to close by going back to the GARVAN Institute for a couple of minutes. So Dr. Warren Kaplan is their Chief of Informatics, and a couple of quotes. One thing that he said is that thanks to Panasas's exceptional performance, our sequencing data stays in a central repository throughout the analysis. So this is the changes in the workflow that I talked about earlier. So this streamlined workflow saves time and bandwidth, enabling us to deliver results quickly to researchers around the world. Panasas lives up to its promise of terrific performance with negligible maintenance and administration time. So typically, the immediate thing that our customers notice is the fact that the performance issues that they were running into in the past have disappeared. But then what they see on a day-to-day basis is how easy the system is to manage. And we have countless customers who have first come to us because of the promise of performance, but then come back to us because of the ease of use and manageability. And that turns out to be, I would argue, the most important aspect of a data storage system. So with that, I would like to invite everyone in attendance to please visit our website. So if you visit www.panasas.com, and particularly the Why Panasas section, we'll further elaborate on the advantages of deploying Panasas in your environment. We also have the GARVAN case study with more details on how they've deployed Panasas storage available under our Life Sciences section of our solutions site. So with that, I'd like to thank everyone for attending, and we're now going to I'll turn things back to Andre for any questions. If anyone here on the call has any additional questions, please feel free to type them into the Q&A portion of your browser.
Thank you very much, Geoffrey, for that very complete overview of NGS workflows. We do have some questions here I'd like to share with you, and you could provide some brief answers for our visitors in this webinar. One of the questions is, are there NGS environments that are not a good fit for Panasas? You seem to have covered a lot of NGS environments and show where Panasas is a potential fit. Are there NGS environments that really are not suited for Panasas?
You can use Panasas storage for virtually every NGS environment. Maybe the only example of a place where we would be less suited would be a deep archive where the data is not very active. However, almost all NGS environments have the need for high-performance storage and archive. And if you look at GARVAN as an example, Panasas is not the only data storage solution that they utilize. They also have deep archive storage as well, but they use Panasas storage for all of the data analysis. We are a great fit for the majority of NGS activities and workflows, but there's room for other data storage solutions as well, depending on the need.
Okay. We have another question here that could apply to NGS and actually a variety of industries. The question is, can we handle video workloads and video streaming in the Panasas product?
Yeah, actually, media and entertainment is is a new market, is a relatively new market for Panasas, but one that we've been investing in substantially over the last 2 years, and we've been seeing great traction there. And not only does that apply to media and entertainment, but it also applies to a lot of our other markets when it comes to visualization workflows. And so visualization in the life sciences, where that translates to streaming video, is a great fit for Panasas. We actually support high-resolution formats, and that's one of the points of interest that's really driving our adoption in the media and entertainment space. So yeah, video streaming is a very good example.
Okay, so another question we have here is about multi-protocol access. Can researchers access data from their Windows desktops simultaneously with data accessed by, say, a Linux cluster?
Yes, and this is an extremely tricky thing when it comes to implementing a data storage solution, and it's something that in particular some of the open source solutions on the marketplace don't have a good answer for. So we actually have multi-protocol access between not only our direct flow protocol for Linux, but also SMB for Windows and NFS for Unix. And in all of these cases, we provide a way of mapping all of the UIDs, so the user IDs in Linux, to the SIDs, which are the user authentication model for Windows. So you can map the two of them together, and then the user group quotas apply to the users, regardless of whether they're accessing from Windows or from Linux. And the data, of course, is also available from both places. And we actually have multi-protocol locking, so data can be simultaneously accessed through multiple protocols with the right things happening in terms of cache coherency in the file system. So this is very different from taking an open source file system and putting a Samba server in front of it, for example, because if you take that approach, the data will not be coherent across the protocols. So there may be cached data in one of in the Samba server that hasn't been yet written to the storage. So there can be some intricacies there that are difficult, and also that the user authentication, being able to map that cleanly between Windows and Linux, is also something that requires a lot more smarts in the data storage. So we provide all of that with Panasas.
Okay, another question we have, Geoffrey, can data reliability, data safety be tiered in our system where certain data is given more reliability than other data in our system?
I'm sorry, can you repeat?
Can data safety or data reliability in our system be tiered to where certain data is given higher data reliability than other data in the system?
Right. So I mentioned in passing that we do per file based protection, and it's actually possible to, even though most people end up specifying the desired RAID level on at least on a high level directory basis, you can have certain directories that are for files that are protected in RAID 5 mode, for example, for slightly better performance but less protection, and then others that are set for RAID 6 plus for the maximum in data protection. We also automatically mirror or triple mirror small files and strike large files. There are also some techniques that the file system automatically takes for performance reasons.
Okay, and we have one more question here. They're asking about something that I think they may have seen on our website and in some of the press and media articles. We claim that our reliability actually increases with scale, so that as you add capacity, the data reliability actually increases. So the question being asked is, how do we do that?
So this is a little bit of a difficult question to answer without a whiteboard, but I'll do my best. So if you have if you have 10 drives and you have to store 8 chunks of a file across those 10 drives, most of the drives will contain a piece of that file. So if you have too many drives that fail, pretty much all of your data is going to be affected, because very few files are not going to have 3 pieces of each file on those drives. So in a scenario with only 10 drives, virtually 100% of the files are going to be damaged if you were to have 3 simultaneous drive failures, which is 1 too many for RAID 6. Now, if you increase to 20 drives, and you have twice as much data, you look at any given file, and you pick 3 of those 20 drives to fail. It's now only a 50% chance that those 3 drives that you selected has 3 pieces of that file. Half of the files will only have 1 or 2 chunks on those 3 drives. And then as you get bigger and bigger, the probability declines, which is a good thing. It means that when you have 3 drive failures simultaneously, even though you have exceeded the fault tolerance, the likelihood that those particular 3 drives contain 3 objects from the 10 that are storing a particular stripe is very, very small. And so you end up with, every time you increase the number of drives by 10 times, you increase the data reliability by a factor of 1,000. So that's why you're looking at actually 1 in 200 million files that you would expect to be impacted by the time you have 1,000 drives in a scale-out file system. So it's just taking advantage of combinatorics and the advantages with just how do you work the math in your favor. And when you have linear scalability of the RAID rebuild times, which allows you to minimize the window of vulnerability, and at the same time use this technique of spreading the data in a different way for every file, that means that you're very unlikely to impact many files at the same time. So it's just simply using the laws of probability to our advantage instead of against us.
Okay, well, I think that's all the questions that we have. Thanks so much for addressing those questions, and thanks for the webinar. So with that, we're going to close the webinar and say thanks to all of you for attending. And if you have further questions, you have contact info there in the slides.